In this video we're going to talk about speed of waves, and for this discussion, first of all, I would like to clarify once again that we have two types of motion in wave propagation. There is the simple harmonic motion of the string elements, and there is the propagation of the wave along the string. So first take a look at the motion of the string elements for sinusoidal waves on strings. So if I look at these string elements closely, I realize that they are moving up and down as the wave propagates from left to right. So this is the propagation velocity of the wave. And I know for a sinusoidal wave that's traveling on a string to the right, the wave function has to form y of xt is equal to a sine kx minus omega t plus a possible initial phase, but for this demonstration let's take this phase to be 0. Okay, then we can have the transverse speed of the string elements. We just need to take one derivative of the position of the string elements as a function of time. So this will be minus omega a cosine kx minus omega t. And then we can look at the transverse acceleration. That's the second derivative of their position vectors with respect to time. This will be equal to minus omega square a sine kx minus omega t. So once again, in order to clarify what speed and acceleration I'm talking about the motion of string elements, the transverse speed and transverse acceleration of the string elements. So this is my y-axis here. Now, something I know from simple harmonic motion is applying here as well. So I have the maximum transverse speed is equal to omega times a, and then I have maximum transverse acceleration, it's omega squared times a. And I would like to note here that the maximum speed will occur when this wave element goes back to its equilibrium position. So this string element has the maximum speed. So this happens at y is equal to 0. And the maximum acceleration happens, on the other hand, at the maximum points. So I see the tension on the string being applied here. So I will feel the maximum restoring force that is trying to pull this string element back to its equilibrium position. So I will obtain the maximum acceleration at y is equal to plus or minus y max or plus or minus a, where I will have the maximum component of tension acting as a force, restoring force to the equilibrium position. Now, in order to discuss the propagation speed of the waves, I'm going to make some arguments based on Newton's second law. So Newton's second law gives me a set of expectations for the propagation speed of the wave. What is Newton's second law? Net force is equal to mass times acceleration. So I look at the net force acting on a string element here. So once again I have the tension on the two sides of the string giving me a net force on the y-axis. So that's giving me the transverse acceleration of the string element. So this is for this string element that we are concentrating on. Okay, so that means if I have a large force and a small mass, I'm going to get a large acceleration or large transverse acceleration to return to the equilibrium position. So if I have high tension, that means I will have a higher restoring force. Therefore, I'm going to get a high transverse acceleration and faster return to equilibrium. Equilibrium point y is equal to 0. On the other hand, if I have a high mass per unit length, mu, that is the mass of the string divided by its length L, if this is large, then I see that the transverse acceleration will be small. So this will go to low transverse acceleration and lower speed of the wave. So this gives me the following conclusion: the propagation speed of the wave depends on how fast the string elements can return to their equilibrium positions, and it should be proportional to the ratio T over mu, tension divided by mass per unit length, to some power n, which will be determined by using dimensional analysis. Okay, so if I look at the dimension of tension, tension is a force, so it is mass times length divided by t squared, time squared. This is kilogram meters per second square. That comes from Newton's second law, F equals ma. The dimension of mass per unit length is m divided by L. So if I look at the dimension of the ratio T divided by mu, it is m L divided by T squared times L divided by m. So it is L squared over T squared. What is the dimension I'm looking for? The dimension of propagation speed is length divided by time. It's dx dt. So this means I can get this dimension if it is the square root of t over mu I'm looking at. So the propagation speed, according to this dimensional analysis, is some factor multiplied by square root t over mu, but in fact we will find that it is exactly equal to square root t over mu if we do a more rigorous calculation. Okay, so this is the information I obtained from dimensional analysis. Now I want to look at a wave that is propagating to the right with velocity v. I'm picking a string element with arc length delta s, a small part of the string, and in the reference frame of the string, the wave is actually propagating to the left, right? Because the string element has to be moving down, so it will be basically performing part of a circular motion, moving down, so that the wave will propagate to the right. So it's in this reference frame, the wave is propagating to the left. The velocity vector is to the left. So if I concentrate on the string element here, I see that this is part of a circular arc, and the circular arc has a radius r. So if I take the midpoint of the string element and find the angular separation between the two endpoints, it's angle 2 theta. So I have here an arc that is produced by two radius vectors r. Total angle is 2 theta. Total angle is 2 theta. And I'm looking at this arc length here. So what is this arc length? So this will be equal to r times 2 theta. So delta S, the arc length, is r times 2 theta. And what is the mass of this string element? Mass is mass per unit length times delta S. So this will be equal to 2 mu r theta. That's the mass of the string element. Now, on the other hand, I have the tension being applied on two sides, on the two ends of the string. So I can see here that there will be a component of the tension in the radial direction. So I will find, if I take a component of the tension here, I will find a radial force, Fr. So what is this radial force? The radial force Fr is equal to 2t sine theta. Now, if this pulse height or wave height is small compared to the length of the string L, so that means I have a small disturbance on this string, right? So it has a very large length, and then I have a very small pulse height and very large length like this, and this pulse is propagating to the right. So in that case, there is a small disturbance on this string. So the pulse height is small. That basically applies that the tension T is unaffected by the presence of the pulse, and the angle theta that I'm talking about for this string element is going to be, theta will be small. So for small angles, I know that I can write the radial force as 2t, approximately 2t theta, theta small. So the radial force in circular motion must be equal to mv square over r, the tangential speed v square over r, and basically this implies 2t theta is equal to m, which is 2 mu r theta v square divided by r. So I find that these 2's cancel, the thetas cancel, and then I get rid of the r's, and I find v is equal to square root t divided by mu. And this is going to be true actually for any pulse shape that travels along this string, as long as these two conditions are satisfied. The pulse height is small compared to the length, and so that I have the tension unaffected by the presence of the pulse, and the theta is small. So I have a small disturbance compared to the full length of the string.